This is Brian Putt, and this video is the second part of a four-part video. In the first part, we introduced the case study and discussed the storyline. In this video, we're going to talk about the Excel model, and we're going to optimize the reference case. And in subsequent parts, we will do the value of perfect information and imperfect information. Here's the top of the model sheet. We have a lot of decisions to make. We have to decide whether we're going to conduct a survey or not. In the reference case, we do not conduct a survey. The model is set up to do both probabilistic and deterministic. We'll just stick with the probabilistic for now. And we have a decision policy with no information. Basically, what we're trying to do here is to calculate the optimal ticket price when we have no information on the demand. These are used for the imperfect information. We'll talk about those later. We have various uncertainty costs that we've already talked about. The fixed cost to perform the play. We have variable cost per person attending. And we have the cost of the survey, which will come in later as well. There's also the capacity of the theater. The demand curves, we've already looked at. This is just describing those demand curves. And then we get down to the actual, based on the ticket price that we've selected, what is the demand? We talked about having an uncertainty around each of those high, mid, and low demand curves. And this is where that confidence interval is specified. It's 20%. The probability of each of these demand curves is shown here, 20, 50, and 30. And so eventually you come down to a deterministic case. So this is one of 1,000 simulations. This happens to be simulation 50. And if I hit this little up arrow key, we get different simulations. This can go all the way up to 30, or it can go back down. Okay? And all these results are changing based on the uncertainties we have. But in this case, the ticket price is always $49.77. So in this particular case, we had a loss of $17,900. I went to a different one. Here we have a profit of $45,000. So let's look at the probabilistic results down here. The net profit for this reference case right now, we haven't necessarily optimized the price yet, is $28,006 with a P10 outcome of minus 23,000 and the P90 outcome of positive 65,000. And you can see the range of tickets sold. Remember, we had a maximum of 35,000 tickets we could sell. So let's look at the dashboard over here. So over here at the dashboard, this is going to be the inputs that we can use. Here it says perfect, and we can also specify imperfect. Well, excuse me, information. Here we can specify information, yes or no, and if we have information, the type of information. And we're going to record various optimal cases down here. So what do we need to do? Oh, let's look at these graphs. This is the graph of the MPV dollars we would get. So you can see there's a 30% chance we lose money and a 70% chance we make money. We can make as much as, I guess that looks to be about $75,000. There's kind of a flat spot in here. So the implication being that this is the low demand. But if I get onto the mid or the high demand, then I'm up on this portion of the curve. If I look at the number of tickets sold, you can see it has a similar shape, except over here, it's vertical because I have a maximum of 35,000 tickets. Note that on both of these graphs, there are actually two lines, a blue line and a dashed black line. The black dashed line will be our reference case, and the blue line will be the current active case. When we get to value of information, we'll have that. So the way the model works is using a data table. This is all part of SIP math. We don't have to really deal with this too much. So I think I'm going to leave it at that as far as describing the model. Now let's optimize our model. So to start with, let us put in a price here of $40. Okay? So someone says, I want to make sure that the theater is full. And we can see that based on the $40, our expected value is $18,000. Looking back here at the graph, here was going to turn out to be our reference case. And here is what it gets at $40. So we have less downside, but also less upside. And here you can see what happened to the tickets sold. We sold many more tickets. We sold out more than 50% of the time, whereas in this reference case, it was only 20%. So we can see that we have different answers depending upon the ticket price. And down here, we are, let's see, I guess these red dots are actually picking up the, I'll tell you what we'll do. We'll come over here and just set these equal to the price that we put in here. Okay, and so now we have down here, we can see where we stand on this demand curve. At $40, we would sell about 2,500 tickets in the low demand, and we'd be able to sell 5,000, except we're limited to 3,500. So now let's optimize our model. What we want to do is to change this ticket price to maximize our expected value down here. So we go to Data, Solver, and remember this net profit down here is not a single number. This is an average of 1,000 things. So we go up to Data, Solver, and we're going to maximize D78. Okay, that's what we want. There's the net profit. By changing this ticket reference price, and I think we'll find the ticket reference price up here. Here's the ticket reference price. We have really no constraints, so I think we're good to go. We'll say solve, and a return to value. And there's the 49.77, which is what I had previously recorded over here. So that's how we can optimize the reference case, and we'll use that reference case in parts 3 and 4 of this video series. Thank you for watching.